less than or equal than the limit inferior of the integrals. Correct? Yes or no?
Mm-hmm.
In other words, the integral of f of d mu is less than or equal than the limit of f and d mu. That's almost what we want. If you take a look in problem number 1, what is what we want, guys?
Integral e f d mu.
Equals the limit, not the limit inferior, right? And not less than or equal, we want equal. So we apply again Fatu. But this time I apply it to E complement, so we have the integral f of E complement d mu is less than or equal than the limit of the integral of fn on E complement. So now I separate this integral as the integral of f minus the integral of E. I, split it. So this is the same as the integral of f on the universe minus the integral of f on E. And the reason we can do this is because why can't we do this? Because this integral is finite. So therefore you are subtracting finite numbers. So your professor, this one is finite, but how about this one? And you're right. The integral of f mu on E is less than or equal than the integral of f on the universe, which is the same as you can erase the universe, and that's finite because of that. Therefore, each of these is a finite number. So this is finite, and this is finite. That's less than or equal than the lim m. You split this as the integral on the universe minus the integral on. Do you remember that we did this in class, guys? I was explaining this. Maybe it was at the end. How's your morning, guys?
Excellent. Thank you.
Likewise, we can split this because this is going to be, these numbers are going to be finite after some n, because this limit is finite. Maybe the first 5 million pieces, the integral is infinity, but because the limit is finite after some n, those guys are finite. Right, Victoria?
Mm-hmm.
So this is true after some n, and because we're taking limit inferior, it doesn't matter after some n pieces. So this is finite, and this is finite. Now, the lim inf of something is less than or equal than, so I think we are using the fact that the lim inf of an plus bn, if you wish we can put like a minus here, is less than or equal than the lim inf of an plus the lim sup of bn. I think that's the lemma. Do you guys remember the lemma?
Mm-hmm.
Yeah.
That's the lemma. You cannot put lim inf in both sides. It has to be.
Isn't it when they have a negative though, Professor? An minus bn? Then you take out the negative, it turns the lim inf into lim sup.
Oh yeah, that'll be another one. Hold on, is that hold on, maybe I'm wrong.
There's no negative in there, it's negative lim inf to lim sup.
Yeah, we can do that later, but right now I'm only applying this one. Well, it can be the other way around. It can be the other way around. It can be this one and this one. Yeah, because we can switch them. So therefore, this is less than or equal than the lim sup of the integral of f n d mu. Or it's even less than or equal than the lim sup. No, wait, no. That's good. So if I apply this here, it would be plus, you guys agree? Plus lim inf of minus the integral, and this is what Eric is talking about. There's a minus here, right? Now, but when you have a minus, a limit, when you have a minus, this minus can travel outside, but it reverses. You know, when you multiply by minus, it reverses things. So this minus, when it goes outside, it becomes lim what? Lim sup. So this is equal to lim sup of the integral of f n d mu minus lim sup the integral of f n e d mu. And then we finish saying, why do we finish here? Because this limit exists. So when the limit exists, it matches the lim inf and the lim sup, so it doesn't matter which one you put. The lim and the lim inf and the lim sup are going to match. So this is equal, in fact, to the integral of f. So this limit exists and is equal to, by that, say by 1, this is equal to what? Integral of f d mu. So what is the conclusion? Conclusion, this is less than or equal than that. You guys agree? So this is less than or equal than this, less than or equal than that, and blah, blah. So therefore, this minus the integral of f d mu is less than or equal than the integral of f d mu minus lim sup of the integral of f n d mu. So this cancels out because this is a finite number. You can, by the cancellation law, you can cancel it in both sides. And then you multiply by minus. Or I would suggest you move this to this side, move to that side, instead of multiplying by minus, which is the same thing. So therefore you have, what do you have after that then? After cancel this, cancel that, move this to the left, move this to the right, so it is positive. So I have, what? Lim sup of these integrals. Oh, hold on.
It should be an E.
There should be an E.
Yeah.
And here too, right? Yes?
Yep.
E d mu is less than or equal than the integral of f d mu.
E.
Right? E. So if you combine this box with this box, you get it. So let's call this star. So by star, the integral of f on E is less than or equal than the lim inf. This is by star. So when you combine this, you finish the problem. Just put these two things together and that's it. This is less than or equal than the lim inf, which is the lim inf is less than or equal than the lim sup of whatever, right? In other words, the infimum is less than the supremum. So Fn mu. Therefore, by the squeeze theorem, this matches that, so they are all equal. Hence, by squeeze theorem, by the squeeze theorem, what do we get, guys? That the lim inf matches the lim sup, right? And when the lim inf matches the lim sup, the limit exists and it's equal to either of those. By the squeeze theorem, so we have that the integral of f on e d mu is equal to the lim, and that's what we wanted. All right, let's do, which problem do we use from, do we do from chapter 5? 1, 2, 3, 4. How about the first one? Do you understand, guys? F is in L. I'm just going to abbreviate it. And lambda of E, we define it by as the integral on E f d mu. That can be positive or negative, because f can be positive or negative or both. Where E is as an element in sigma algebra. So show that lambda of E is greater than or equal to 0 if and only if, this is true for all E. So for all E in X, lambda E is greater than or equal to 0 if and only if and only if F is greater than or equal to 0 mu almost everywhere. So let's do one direction. Here the trick is to check that a number, think of a number is great, forget about the function. Think of this fact, a number is greater than or equal to 0 if and only if, any number that you can think, if and only if that number is greater than, so actually let's do it the other way around. A number is less than 0 if and only if the number is less than
Or equal to 0 and doesn't equal 0, is that what you're saying?
no, just that x less than 0 if and only if x is less than a number of the form -1 over n. Not, I mean, it's if and only if there is an n such that the number is less than -1 over n. Does it make sense or not, guys? Because if there's an n such that x is less than -1 over n, and because this is less than 0, by transitivity, x is going to be less than 0. Now, the other way around, if x is less than 0, here is 0, here is x. So the numbers -1, or -1 is here, -1/2. At some point, you get -1 of n. At some point, x is going to be less than -1 over n. Do you guys agree? So that's true. Based on that fact, you consider the set A equals the points in the universe such that f of x is less than -1 over n. All right? And we apply the usual technique. We're not going to write, we're only going to watch and then you write it, okay? Here we go. So what happens on A? On A, what happens? Who's bigger? F of -1 on A. For x in A, what happens? On A, f is less than -1 over n, right? On that set, in other words, for x in A, f of x is less than, yes or no?
Yes.
Therefore, in general, the technique is hence, in general, multiply, this is true, multiply by the characteristic function of A, and that's true regardless. You see what I mean? Yes? That's called the technique. You build a set, and on that set something happens, you say therefore in general it's true. Now that this is true, you take integrals in both sides. Right? V mu, oh shoot. V mu less than or equal than 1 over n times the function of a d mu, right? So you take integrals in both sides. And then this integral is very easy to do. What is this integral? Equal, this is a simple function. This is like a number. Imagine like 5, the characteristic of 2,9. What is the integral of that?
35.
It's 5 times the length of the integral, or the measure of this integral, right? So likewise here, what is this integral? Negative 1 over n times the measure
Of it.
of a.
Wasn't that strictly less than on the?
No, it's less than or equal, because when you have a function less than another one, the integral is less than or equal, because the integrals actually might be equal. So you have the zero function, you have a function that has only one dot.
So even though we had that strict inequality in the previous step?
Oh yeah, you can look here. It doesn't. This one it doesn't matter.
No.
This one doesn't matter. All right. So, oh, by the way, this integral is what? It's this thing here, right?
Yeah,
You see it?
yeah, it's 1 over n.
So this is equal to what? The
Right.
integral of f d mu on a, right? This a goes, right? And this is the same as lambda of a. But lambda of a, I'm going this direction, therefore I'm using this as my hypothesis. This guy is greater than or equal to 0. Therefore, this guy is greater than or equal to 0, right? But look at this. This guy is positive or negative?
Positive.
Well, greater
Or
than or equal to 0, right?
Okay.
But you multiply by a negative number, this is less than 0. What happens when you multiply a positive number times a negative number? That's less than or equal to 0. Again, by the squeeze theorem, what happened by the squeeze theorem?
Everything is 0.
So everything's 0. So in particular, this guy is 0, right? You agree?
Yeah.
So by squeeze theorem, like this is not 0, so this has to be 0, right? Lambda, no, what? Mu of a equals 0. I didn't want to tell you because I didn't want to scare you, but this set depends on n. You guys agree? I mean, there is an n right here, but if I put the n, people will get scared. Now just think, this set depends on n, right? So this is true on n. Now that you know that, what I know is that all these sets have measure 0. And so it's time to recap, say, what is what I wanted? What is what I wanted? I wanted to prove that f is greater than or equal to 0. And what does this mean? It means there exists, this means what? There exists a set in the sigma graph of measure 0 such that outside of that set, for every x outside of the set, f is greater than or equal to 0, right? Yes? So in other words, I'm looking for a set. I claim that I found it. I found the set. So I found the set. And the set n is equal to the union of all these guys. Now clearly, what is the measure? But why is that? Okay, so 2 items. If I prove this and this, I'm done, right? So 2 items. Number 1, I want to prove that the measure is 0. What is the measure of n? It's the same as the measure of the unions. So let me see 2 items here. And with those 2 items, we'll finish. So first item is the measure is 0. So some people are tempted to write here equals the sum of the measures of an. I say each of them has measured 0, professor, so therefore the whole sum is 0. And you're right. But the question is that that's not true unless they are disjoint, right? We don't know. But what is true for sure is that the measure of any union is less than or equal than the sum of the measures. So it doesn't matter. So this is 0, that forces n to be 0. You see what I mean, guys? Therefore, well, the measure of n is greater than or equal to 0. By the squeeze theorem again, so then by squeeze theorem, the measure of n is 0. And the second item is that I wanted to prove that outside of that, the function is greater than or equal to 0. But that comes from this fact that you agreed at the beginning. That comes from this fact. A number is less than 0 if and only if there exists an n such that x is less than or equal to -1 over n. So this there exists transforms into a union or intersection?
Union.
Union, right? If you have for all, that's intersection. But this there exists means a union. So therefore, the set of points where the function is negative, by using this fact, is the same as the union. So if something is negative, therefore there exists an n such that what? This just translate that into this union. So f of x is less than 0. Forget about x. You can call it f of x. F of x is less than 0. Therefore, there exists an n such that f of x is less than or equal to -1 over n. Now, who the heck is this set? Who the heck is this set? Do you what's the name of that set? A-n. And who the heck is the union of A-n? What is the union of A-n? N, right? The union of A-n is capital N. Conclusion, what happens on n? What happens on n? F of x is less than 0. And what happens outside of n in the complement of that? F of x is greater than or equal to 0. See what I mean? In the complement of that, hence, you say hence, for x outside of n, outside of this set, the complement of this is the opposite. F of x is greater than or equal to 0. All right? Take a look. We first we write this fact, and this fact you can put it in your in your cheat sheet if you wish. You build a set and you apply the technique. What is the technique? On that set, this function is less than that. Or you can put less than or equal if you wish. Therefore, you take integrals in both sides. One integral
about
is
in being extracted in alcohol, but
That's science, right?
That's good.
I don't know why I started playing.
Music does.
That's weird. Sorry.
So on this set, you apply the usual technique, take integrals in both sides, multiply by the characteristic, take integrals in both sides. This integral is easy. And this, you use the hypothesis. And therefore, by the squeeze theorem, all of them are 0. In particular, this guy is 0. And then you say, I found the set that I was looking for. My set is n equals the union. Why union? Because it says here there exists. Remember, union is associated with there exists. An intersection is associated with for all. You have to remember that, right? Go ahead and try to write it on your own, guys, without looking at the board. And if you cannot, then look at the board and see, oh shoot, I forgot that, okay? In this way, you will be very, very ready for the test. The other direction is easier. It's more intuitive and faster. So it's the same technique so I know that f is greater or equal to 0, right? So f greater or equal to 0, mu almost everywhere means or implies that there exists a set in the sigma algebra. Let's apply the same technique, guys, and see if you can understand it. The measure of E is equal to 0 and outside of that of that set, or let's say some people prefer for every x in n complement, f of x is greater than or equal to 0. Yes? Okay. Now, another technique that another tool that we're going to use is the following. Lambda of E is the integral of f on E by definition. But how do we define the integrals of a function on E? We define it as
F plus
f
d
plus
mu minus
mu minus f minus d mu. And because this function is greater than or equal to 0, this is for sure, it's like lambda plus, it's like this is for sure a measure evaluated at E, right? See what I mean? When the function is greater than or equal to 0, that becomes a measure. That's one of the lemmas in the book. So because this function, it's evaluated at E, this is greater than or equal to 0, this is also a measure evaluated at E. So you say, oh, therefore difference of a measure is a measure, and therefore this is greater than or equal to 0, professor, and we'll finish. No. Because the sum of the measures is a measure, right? But the difference of a measure is not necessarily a measure, right? So that's the point. But now take a look of this. So because this is a measure, this measure is absolutely continuous. How do you say absolutely continuous with respect to mu? Remember? This measure of E, this measure, let's just put it like this. Let's call it lambda plus, okay guys? Lambda plus of E is absolutely continuous with respect to mu. That's another lemma. And this lambda plus minus is absolutely continuous with respect to mu. All right. So we have all the ingredients, and we just put them together, and that's it. So on n complement, what happens? Tell me yourself, guys. On n complement, what happens? On n complement. For x in n complement, what's bigger? F is greater than or equal to 0, yes or no? So you kind of erase that, right? Hence, in general, it's the same technique. Try to memorize the technique. Danny, we're trying to apply the same process, like we're just watching and then we force ourselves to write a little bit. So, on n complement, this is greater than 0. So in general, what happens? In general, what happens in general? F times the characteristic function of this set. See what I mean? Is greater than or equal than 0 times the characteristic function of n complement. Just take integrals in both sides. You see, Robin? We're trying to just force ourselves, right? Here we go. I'll give you time to write, no worries. d mu. Now this integral is very easy to compute. What is the integral of this function? Just 0. 0 times is 0, right? See what I mean? So therefore this integral is 0, right? In other words, we do the same thing that we did before. This is the same, this n goes down, so this becomes what? The integral of f on n complement d mu is greater than or equal to 0, right? And that's it. Now we finish. So what is the integral on the e? What is what we want, guys? What is what we want? We go this arrow, so we go this way. We want to prove this. Yes? So let's go ahead and let's compute lambda of E is equal to the integral on E of f, yes? d mu. But do you agree that this is the integral, this is the sum of two integrals? And see if you can help me. This is the sum of two integrals. Not the difference, the sum of two integrals. What goes here and what goes here?
E complement. Or no,
Intersection. Think like this. Think like this. This is E. No, my picture is small. Think this is the universe. This is E. And there are two sets. N and N complement. So this set E can be seen as the union of two pieces. What are those two pieces, guys? E intersection, this is E. E intersection N and E intersection N complement. No, I am claiming that one of them is greater than or equal to 0. One of these integrals is greater than or equal to 0. Which one is greater than or equal to 0? This one, right?
That's greater than
Because, oh shoot. So maybe I should have done it. On N complement intersection, you see what I mean, guys? On N complement intersection E, what happens for sure? F is greater than or equal to 0, right? So why is that? Because the points that I'm taking, they live in the intersection. And if they are in the intersection, they also are in N complement. You see what I mean? Do you agree, guys? If you take a point in this intersection, it's for sure in N complement. And when it's in N complement, for sure the function is greater than or equal to 0. So, sorry. So instead of that.
Dr. G, can't you just still keep it that way and it's the same idea? If it's true on N complement, then it's going to be true on anything intersecting.
Yes, yes, but some people say, I want to make sure that everything is right, Professor. Okay, I know. So therefore, this piece is greater than or equal to 0, right? And this piece is 0. Why is that 0? Because this is where I use this piece right here. Split it into integrals, right? Split it into integrals. What is the first integral? F plus d mu E intersection N. Do you guys agree? And the other one is F minus d mu E intersection N. Now look, take a look at this. What is this? How do we call this? Lambda what? Lambda plus of what? E intersection N, right? Which is less than or equal, because it's absolutely continuous, this less than or equal than mu of E intersection N. Well, it's not less than or equal, but this guy is 0. Do you guys agree that this is 0? This is 0. Why is this 0? Because the measure of E is 0, so the measure of something smaller is also 0. When this is 0, that implies that this guy is 0. Likewise, this is lambda minus of E intersection N, but because mu of E intersection N is 0, and mu is absolutely continuous, that implies that this is equal to 0. Therefore, this piece is 0, and this piece is 0. Therefore, this piece is 0. Therefore, this is, in other words, this kind of cancels out. You see what I mean, guys? Yeah. So therefore, this piece is greater than or equal to 0. And we finish, yes? All right, try to write it on your own without looking. And if you don't think, a number y is greater than 0 if and only if, just a number, just think of a number greater than 0. If and only if what? Y is greater than what? Y is greater than
Or 1 over N.
Yeah.
1 over n, right?
Yeah.
So, 1, let's not write that. Let's not write that. Let's just pay attention. Look. Yes or no? But what goes here? For all or there exists? There exists an n. So based on that fact, we can finish the problem very easily. Look. So this is what I want this time, right? So therefore I build the sets, let's call it A equals the x in the universe such that f of x is, let's call it greater than or equal. Greater than or equal than 1 over n. And tell me yourselves, on A, what happens on A? That's the technique. On A, what happens? Who's bigger? F is greater than or equal to 1 over n, right? Therefore, in general, what do I do? Therefore, in general, see, you're getting it. You're going to ace this test. Look, okay, just follow it. F times the characteristic function of A is greater than or equal to, I'm going to be careful. I'm going to leave a little bit of room. Times 1 over n times the characteristic function of A. And you say, so what do we want, Professor? We want to show that this is sigma finite. What does sigma finite mean? Let me erase it. What does sigma finite mean? That this set is the union of some sets, right? Some sets. Bn's from n equals 1 up to infinity. And the measure of those guys is finite. That's what sigma finite is. Remember? Sigma finite, can you? Yeah, all right, that's what I want. So what do I do in both sides, guys, now? Take the integral, this is the mu, this A goes downstairs, and this is pretty easy to compute. What is this integral? 1 over n times the measure of A, and I'm lying that A depends on n, right? So now you feel less scared, and this n goes downstairs or not?
Okay.
Yes? Hold on. Okay, good. This goes downstairs, right? This is equal to what? The integral of f on what? And d mu. But this is less than or equal to the integral of f on the whole universe, which that integral is finite, right? It's finite. Conclusion. What is the conclusion? What is the conclusion? This quantity is finite, right? That. Watch. This quantity is finite, right? So therefore, mu of an is, I can write it this way or this way. Let's write it. It's finite, right? So I found the set. What is, oh no, I already have the set. So therefore, the union of this, what is the union like? The union of these guys, the union of an, the union of these pieces is the same as what? What do you think, guys? Let's write it, if you wish, nicely. This is the x in x such that f of x is greater than or equal to n. So by this fact that you agreed at the beginning and you signed it and you said, yeah, I swear on my life that this is true, there exists y greater than or equal to n, there exists an n such that this is greater than or equal to 1 over n, is the same as the set. This there exists greater than or equal to n is the same as the set x in x such that f of x is greater than 0. Conclusion, what did we achieve? This guy equals the union of some sets, we can call it ANs if you wish, right? And the measure of this, of each AN is finite. Therefore we finish, right? You see what I mean, guys? Alright. Like do it that should be faster for you to do. Okay? Try to force yourself to do it like if you were in the test. And so let's do this one, and I have a strong feeling about this problem, guys. So if f is in L, that's the next problem number 2, chapter 5, and epsilon is greater than 0. Therefore, there exists a 5 simple measurable function such that the integral of f minus 5 d mu is less than epsilon. And so for this problem, we're going to use the following fact. You have here the supremum of a set, and the supremum is finite. It's like a real number, right? So that this is real number, right? And you go a little bit behind the supremum, like supremum of A minus some number, delta. For sure you can find right here, for sure you can find an element A in the set, for sure. That's one of the properties of the supremum. And the reason that this is true is because this guy is not a lower bound. Because if it were a lower bound, the supremum of A would not be the least. I would have found a number that is less than the supremum and it's still a lower bound, an upper bound, I'm sorry. So therefore, this guy cannot be an upper bound. If it's not an upper bound, there exists an element in the set that is bigger than that. That's the set, right? So that's a fact that we're going to use. And why? Because we have an epsilon here. All right, so the proof goes like this. By definition, f plus, the integral of f plus d mu is, who remembers the definition of a greater than or equal to 0 function? It starts with the supremum of integrals of phi d mu such that phi satisfies lots of conditions. What are the conditions? Phi is greater than or equal to 0, less than or equal to the function, right? And phi is simple, measurable, right? Yes? So if I use that fact, so here is the supremum, right? This is my set A. This is my set A. So if I use that fact, but watch out because this is like, this picture is the key to everything. So this is the supremum of A. And if I go before like the supremum of A minus epsilon over 2, you might say, Professor, why epsilon over 2? It's because I need 2 of them, and at the end, I want them to add up to epsilon. Why do I need 2? Because I'm going to need one for f plus, and I'm going to need another one for f minus. Get it? That's the reason I have epsilon over 2. So, by that fact, there exists what, guys? There exists an element in A somewhere here, right? Now, question for you. How do the elements how do the elements of A look like? Are they cars? Are they integrals? Are there, say it again?
They're all simple.
No, the elements of A are integrals, right?
Yeah.
Integrals of functions. These are the elements of A, right? So therefore, say it again?
They're all numbers.
They are numbers, right? But they look like integral of something. You see what I mean? So here there is an element. So here there is like that, right? Where mu is what? Where phi is greater than or equal to 0. Well, we can say that in words. So hence, so by this supremum property, tell me, there exists a function phi that is greater than or equal to 0, less than or equal to f plus, right? And phi is simple and measurable, such that the integral of this is greater than what?
Greater than
The supremum of A minus epsilon 2. But what the heck is the supremum of A? What is the supremum of A equals to? The supremum of A is equal to the integral of f plus d mu minus epsilon over 2. Do you guys agree? Yes? Likewise, by the same argument, just mimic it, guys, what I say, by this, but do f minus instead. What is it? By the supremum property, Dmitry, I'll give time to write, okay? There exists what? There exists, a function, right?
Yeah.
0 less than or equal to 5 less than or equal to, hold on. You cannot call it the same,
Yeah,
you see what I mean?
awesome.
Let's call this something and let's call it something else. Let's call it this one 5, 5, 1. Let's call this 5, 2. What else? 5, 2 is
simple, measurable.
simple, measurable, such that what?
The integral.
The integral of f minus d mu is minus epsilon over 2 is less than the integral of 5 to d mu. Now this epsilon over 2, we can leave it on the left or we can move it to the right as positive. You see what I mean, guys? It's better to move it on the right, but let's do it like that. So we finish a problem. Why do we finish a problem? Because what's what we wanted, guys? We wanted a function such that this has an epsilon. So the way we do it is just put them together like this. Start with this and put those pieces together. So you write this. F minus 5. Oh, by the way, the function that existed here was 5, 1. The function that existed here is 5, 2. Guess what my function is going to be? Consider 5 equals, look, f equals f plus minus f minus. So what's going to be the 5 that I'm looking for? 5, 1 minus 5, 2. Perfect. Okay, let's put it in. The integral of the absolute value of f minus 5 d mu is equal to the integral. Let's replace f by, guess what?
Plus.
F plus
And then
minus f minus. Let's replace phi by phi 1 minus phi 2, right? And we're going to use these pieces. You see what I mean, guys? D mu and so let's group them together. So this is the same as I'm going to associate which one with which one, guys? F plus minus phi 1, right? F plus minus phi 1, right? Plus F minus F, no, plus minus
parentheses.
F
Yeah.
minus
5,
5, 2. Does it match or does it make sense or not, guys? Let's see.
2.
Because minus times minus is plus, right? Minus times minus. Does it make sense? Yeah?
Yep.
All right. Now, this is like A and this is like B. So A minus B by the triangle inequality is less than or equal than A plus the absolute value of B. You guys agree?
Yeah.
So this is less than or equal than the integral of absolute value like A, which is this guy, right? So it's going to be F plus minus phi 1. And watch out here. Does this inequality say plus or minus? Plus. Sheena, wait, hold on, okay. So I'll give you time to write, okay? This is the learning time. Plus the integral of f minus 5, 2. My question for you, is this quantity inside the absolute value positive or negative, and why?
Positive.
It's positive. Why is it positive?
It's if we subtract it over there. Yeah.
Phi 1 is for sure less than or equal to f plus. That's the reason this is positive. Now, likewise, this quantity is also positive, right? So this is greater than or equal to 0. And this is greater than or equal to 0. What is the absolute value of something greater than or equal to 0?
Itself.
Just the quantity itself, right? So this is just f plus minus phi 1 v mu plus f minus phi 2 v mu. And this integral, the integral of f plus minus the integral of phi 1 is less than epsilon over 2. You see what I mean, guys?
Yeah.
So this is less than epsilon over 2. And likewise, the integral of f plus minus the integral of phi 2 is less than epsilon over 2. So this quantity is less than epsilon over 2. Conclusion, the whole thing is less than epsilon. Now you have time to write, but try to not look, and if you cannot, then you look at it, okay guys? I'm giving you time for sure to write. All right.
With the weak epsilon number 2 proof.
All right, so let's do D. So it says find. Oh, you might get scared of this because it has 3 items.
No, it's just the find. Because I think that's an example, right?
Find, yeah.
And
The only one is find a sequence of functions fn in n plus, and f, you have to find m in n plus,
I'm not scared.
and a set E in x. And you have to find, you have to find x, and mu. You have to find all those things such that, number 1, fn converges to f. Number 2, the integral of f v mu is the limit of the integral of fn d mu. The integral of f e d mu is not the same as the limit on E. I think in English what you want is you want to find a sequence of functions and a set such that kind of the areas, the overall areas match, but the areas on a specific E or on the top of an E is not, they don't match. In other words, let's say that this is your function f. The area from minus infinity to infinity, that area, if you think of the Riemann integral, that area is the same as the limit of the areas of fn. I don't know, that's f1, f2, f3, up to they converge to f. So the limit of those, minus infinity to infinity, the limit of those integrals is they match, right? But the integral of the same function on a specific set E, that is not the same as the limit of, on that set E, of like that limit. You see what I mean? Like limit of f1, f2, f3. So you see what I mean, guys, or no?
Yeah.
So that's what we want, a function such that the overall area matches with this limit, right? And but the area on a specific set, it doesn't match. That's what we want. So raise your hand if you have an idea. Yes, Dimitri. So I'm going to give you some items. But you have an idea?
I do,
All right. What is the idea?
but I didn't formulate it yet. So the idea is that we're gonna choose some set E such that the function is gonna be mu, 0 mu almost everywhere type of stuff. So that when we take the sequence of the functions up to the limit
Mhm.
and so we gotta find a way. We gotta define the sequence of functions in such a way that each of those little ones would be dropping down to 0 because
They kind of put
Something
down to
like-
0?
something like one of those guys when you have an entry point and your value is right here, so that
Mhm.
your function over the set E is gonna have some value, but your sequences are gonna have 0 values at each of those. But this is for a singleton, and we just need to, by the eraser rule, we just need to make those thingies a little wider. It's like we need to shrink this to the set E.
Okay. That's a good intuition.
I like your eraser rule.
Also eraser and fill it in, right? It's like take a point and shrink,
just-
Yeah.
shrink
So
it
what
up to
you-
that set.
What I'm going to do is I'm going to give you like this. This is a real number. These are maybe you can do Borel,
Well, makes sense.
and this is Lebesgue. Now you just need to find Fn, F, and E. So what I mean? So the measure of mu is the Lebesgue measure. So you just need Fn, F, and E. If I give you this, probably you can get these two easily, but I think this is the hardest one. So we need functions such that, and here we have lots of possibilities. We can think about it, we can make mistakes and change it, mistakes and change it until we get it. Or I can just give you the final answer and then you just. Okay, so I will propose one of them. So first I'm going to say that if this integral is finite, then we cannot. If this integral is finite, we cannot solve the problem because there's a problem in the book saying if this converges to f, this f is the limit of the integrals and it's finite, then no matter which e you choose, this is always going to be true. So what we're looking for are functions such that we want this integral to be infinite. Otherwise, we cannot solve the problem. In fact, it's impossible to do the problem. So we want for sure that this area is infinite. You see what I mean? Infinite area. Because in fact, that's a problem that comes from another one. Say, show that if we remove the finite property, the problem is false. So we want this infinite. That's what we want. So I'm going to propose one that is not going to work. Okay? So let's do n times the characteristic function of 0, 1 over n. No. 0, 1 over n. But there's only one problem with that function. First, let's take a look of how does that function look. The first function
It goes from
is
0 to
goes
1.
from 0 to 1. You guys agree?
Mm-hmm.
And the height is 1.
1,
And outside of it
0.
is 0, right? And it doesn't matter the dots if it's here or here. It doesn't matter because the Lebesgue measure of a singleton is 0, so it doesn't matter. Right? So that's F1. Do you guys agree?
Mm-hmm.
What the heck is F2?
It's from 0
So
to
maybe
1.
you cannot solve. Maybe you cannot find the functions, but for sure you can tell me who is F2. How does F2 look like, guys?
It's from 0 to 1 half.
It's from 0 to 1/2,
And it's at 2.
and the height is going to be 2. Wow. Right? And then F3, I'm going to do that. That's going to be the last one for you to see what's going on.
From 0 to 1/3.
0 to 1/3.
And the height's at 3.
The height is at 3. So what is the integral? What is the area? Remember, we want infinite. But what is going to be what's the area of this function, guys? How much is this? Or the Lebesgue integral. The Lebesgue integral and the Riemann integral, they match. But what is the integral of that? It's 1 because it's base times height, right?
Mm-hmm.
If you don't believe me, you can do what's the integral of 1 times the characteristic function of 0, 1 with respect to the lambda measure is 1 times the Lebesgue measure of this guy, which is 1, right? So the answer is 1, yeah? So in other words, it's base times height. So what is this area? So this integral is 1, or this area is 1. How much is this area? 1. How much is this area right here? It's also 1. You guys agree?
Mm-hmm.
So that's not going to solve the problem because I want this area to be infinite. Otherwise, by the previous problem, it's impossible, right? See what I mean? So, oh, shoot. And by the way, these functions fn that you see here converge to what? These functions fn converge to what do you guys think?
It's either 0 or infinity.
Well, let's take one at a time. Let's take one at a time.
It's going to
So
converge to
let's
0
take
times infinity
fn of,
because we're going
for
to
example, fn of 1. What is the first function evaluated at 1? 0. What's the second function evaluated at 1?
0.
Like it's 1 here and 0 outside. So this is 0, so that converges to 0. How about fn of 1/4?
Yeah.
Well, the first one is 1, right? You see what I mean?
Oh, yeah.
So
But then-
so this is like the sequence is 1. The second one at 1/4 is 1. The next one at 1/4 is 1.
and
But the
0,
but the next one is going to be 0, 0, 0. So that converges to 0, right? What is fn of -7?
It's always 0.
All of them are 0, so this is 0, so that converges to 0. What is the only point that fn of something
It's 0.
doesn't converge to 0? What is the only point? 0?
Yes.
Okay, let's see. What is the first function evaluated at 0? What is this function evaluated at 0? It's 0 because the point doesn't belong to 0, 1.
Oh,
This
that's
is
fine.
excluded, right? So, no. So this
That's
also converges to 0. So the answer is all of them converge to 0. So therefore, fn converges to f identically 0. Does it make sense? Even though this goes up to infinity, but it converges to 0. Like if you look at every single x, fn of x converges to 0. If you look at any single value. So that
Unless-
function is almost the answer, but not quite. We need to add an extra piece because we want the area to be infinite. And these areas, all of them are equal to 1, right? So the limit is equal to 1, and the limit and the integral of f d lambda is equal to 0, right? So, oh shoot. You see what I mean? And they need to be equal, so So this is okay, but this fails and this fails.
What if we
Well,
take
almost get it.
what if we take arbitrarily small epsilon, which is always positive, and then evaluating the function of this epsilon, we always have the
Which function?
oh, similar to the example you just had, the
Uh-huh.
convergence when you take
When you take one, the first one, it's one, and the second one, it's out, so it's zero. So the sequence is going to be 1, 0, 0, 0 for the rest.
No,
But if you take the
yeah,
epsilon,
no.
which is
It
arbitrarily
won't.
small but never zero, so it's
I don't
always
think you meant that.
in this shrinking.
So instead of 1 over n, you propose epsilon,
Yes, arbitrarily small epsilon, which is always.
but that epsilon changes or it's fixed?
Oh, I see what you're saying. There exists an n such that after this
Yeah,
it's
so-
going to surpass that. Okay.
So let's continue at the end. We just modify that and we finish the problem. So how can we modify that, guys? We need the area to be infinite. But those areas are finite, are equal to 1, and in fact the function, the integral is 0 because the integral of 0 is 0. So we need to modify that function.
and
So
times.
we need to add something extra.
I would say, do you want them
Just-
like disjoint intervals?
This
It's like
that this kind of
Oh,
like
moving-
there and then like it goes
Like the contra sets type of
like
stuff.
it goes like enough.
Oh, okay. So you want your first function to be like this. You want your second function to be like this, maybe.
I don't know. That was my guess.
But again, these areas are going to be finite.
Sure.
We need to add something such that the area is infinity.
At infinity. And times scope 2 is a function plus infinity.
Make your interval 0 to 1, 0 to 2.
Make it. Make
What if-
it.
what if
Make
it's 0 to
it.
n?
What if instead of
Yeah,
n
that's what I
becomes
was
n
thinking.
squared?
Well, but is the issue that the inner? Oh, you'll get n then.
Then the area is going to be 1, 2, 3, and the area is going to be infinity. But still, that function converges to 0, and that integral is 0. Oh, shoot. Putting
What if-
that doesn't help. You see what I mean, guys? Daniel said, like, what if we make it a little bit bigger or
What if we
deeper,
make the
right?
interval bigger, like 0 to n instead of 0 to 1?
0 to n,
Yeah.
and then here n, or 1 over n, or just that, or n squared, or just leave it like that. So that, the first integral, this is going to be the first one. The second one is going to be from 0 to 2, right?
Yeah,
But this is going to be 2, so that area is going to be
4.
4. Okay, that kind of works.
And then 0 to 3.
And then 0 to 3,
9.
and then it's going to be 9. All right, so that works. So this is going to be infinity. Good job.
It doesn't. I don't think it matters.
Just to play it safe.
And then, but it converges to what? This function converges to what?
N squared.
Converges to. This kind of looks small, but in
Yeah,
reality
supposed
it's
to be
big. So it converges to the characteristic function of 0 infinity times infinity. So there you go, it's going to be infinity. All right, so good job. This equals that. So this equals that.
Yeah, but it's on some.
But which set is going to be like a weird set where the area under that set is not going to be?
What if we introduce the alternating areas,
Hold on.
positive and the negative?
Let's try to finish this by trying to choose a set E. So maybe we choose the set E to be, I don't know, 5,7 or 5,5, whatever, 20. The integral of the first one on that set is going to be 0. The integral of the second one on that 5 is going to be 0. But at some point, this integral is going to be, I mean, at some point this is going to go super large, and so the integral is going to be infinity, and this one is also infinity. So now,
Oh, what if we do?
What if we do something like -1 to the n, so it's going to be the similar idea. but
no,
something
you
is
want
gonna
them
be
positive in
positive
this
and
in this
negative
problem, right?
like that.
Yeah.
You want them positive. You want them in m plus.
But then take the absolute value of that thing and the set.
Oh,
Some
this absolute
sets.
value matches that. Because it's
Well,
it's
to-
greater than 0.
Take the alternating thingy, -1 to the n, absolute value to make it all positive, but then that's going to flip everything up to the positive side, but then you can choose your set e to be
Oh, you
just
want
the,
you
just
want
the
to
odd.
wait. So you want to change the function?
Well, yeah, that's my proposal. Do the alternation -1 to the n.
Mm-hmm.
So
And
have
take
it
the absolute
flip-
value.
Take the absolute value, so everything is positive.
So it's a 1.
Yeah. Everything,
The absolute
like,
value
everything has to be an m plus.
-1 to the n
Yes, yes.
is 1.
Yes. But then for the set e, we're going to consider just the odd ends, the ones that are flipping it.
But remember, everything we want everything
Alright, absolute
positive.
value is going to.
Yeah.
Okay.
So I suggest we keep it the same way we have it. We just add an extra thing that makes the area infinity. So F1 like that, and add an extra thing that makes the whole area infinity. What is that extra thing, guys?
Plus infinity.
So let's add another line, like somewhere there that makes all the area infinity. What is it? Okay. I suggest we go like this forever. Forever. How much is that area?
It's infinite.
Infinity is base times height, infinity. You guys get it? So the whole area is what? Infinity, right? You guys agree?
Yeah.
Now, this for the next function, we do the same thing, but
But
we
is
go
it
here
down?
forever.
Is it still at like
At
1?
one,
whatever?
yes. This is at 1.
Okay.
So what is this area plus this area?
Infinity plus
Like
1.
all the way together, the answer is
Infinity.
infinity. Yes, does it make sense?
Mhm.
And then here we go at 1 forever. So what is all this area? Infinity plus 1. Hold on, this is not 4. This was 1/2. This was 1/3. Who changed it?
You did definitely.
All right, so this little area is 1, but this area is infinity. You guys agree? This area is 1, but this is infinity, so altogether is infinity. So this little area is 1, but this one is infinity, so altogether is infinity. Yes? Does it make sense? All right. Where does it converge? It doesn't converge. Does it converge? Okay. Think. Where does it converge? Who's going to be? Okay, so that's not the function. Hold on, that's not the function. This function is not. What is the new function? Is the whatever we have, right? Plus, what is the name of this piece, guys?
1.
What is the name of this piece? Yeah, it's 1 times
The
characteristic function of
the unit.
Negative
negative
to 0.
infinity 0, right? We can do 0 like this, they neutralize it with a bracket.
Well, otherwise it's going to be discontinuity.
All right, so where does it converge? Where does it converge? Let's take points and we guess. Let's take, what is Fn of 7? What is this value? Like the first function evaluated at 7?
7
Is-
positive?
Yeah, at 7
Okay.
positive.
0.
Is 0. The second function evaluated at 7 is 0. The third function, this is 0, right?
Mhm.
So that converges to 0, yes?
Mhm.
How about Fn of 2? First function evaluated at 2 is 0. At 2 is 0, so this is 0, converges to 0. This is when you don't know where it converges, you test one point at a time. So what would be Fn of, I don't know, 0.4? Fn of 0.4, the first one is, so let's do it like this. The first one is 1, right? 0.4 is here. You guys agree? So the first one is 1. The second one, 0.4 is here, is how much?
2.
2. The third one, 0.4, is
No, Dr. G.
It's outside
of the interval. 1/3
Really?
is 0.3.
okay. So it's going to be how much?
0.
0. And the next one is going to be,
0, 0, 0, 0.
so it converges to what?
0.
0. Okay, give me another point. Fn of what?
Epsilon.
Epsilon positive?
Yeah,
Okay.
always.
So this is going to be, I'll tell you what the sequence is going to be. This is going to be 1, 2, 3, 4, and at some point it's going to be
0.
0, 0, 0, 0, so it converges to
0.
0. You guys agree?
Yeah.
So how about Fn of 0?
It's 1.
What's the first function evaluated at 0? 1. Second function evaluated at 0?
1.
1. Third function evaluated at 0 is 1. So this is 1. That converges to 1. Fn of negative 3. Fn of negative 3 is
1.
1.
1.
Negative 3, 1. Negative 3, 1, right? So this is 1, it converges to 1. It seems that all the negative points, all the negative numbers is equal to 1, is going to converge to 1. You see what I mean? All the negative numbers, including 0, right? Therefore, what is the limiting function? What is Fn converges to? So you see, each point converges to 0 if it's positive, or right? But if it's negative or 0, it converges to 1. So what is the limiting function? If you graph the limiting function, how does it go? What is the graph of f? So for each point that is positive, the answer is 0. For each point that is negative, the answer is 1. How about 0? 1. So that's the function. So who is this function?
Characteristic function from negative infinity to
This
0.
is a characteristic function from
Negative infinity to 0.
0, right? All right. So this checks. What is the integral of f? What is the integral of that function? What is the area of this function? What is it? Base times half. What's the answer? Infinity, right? Both of them are infinity, so this checks. Now, what is a troublemaker? What is a set that is a troublemaker where the area on that set is going to screw up everything?
Any
Zero.
set within the positive.
E equals what? So, we found f, right? So what is E? So find E. What is E?
Is the interval a to b where a and b
Just
both
0
0 to 1,
0 to
anything.
anything, but
How about just, no, give me a specific one.
0 to 1.
0 to 1. Okay, let's see. What is the area of the first function only from 0 to 1?
1.
1. Does this make sense? What is the area of the second function only
From 0
to 1?
1.
1. What is the area of the second function only from 0 to 1?
1.
So all these areas are equal to how much?
1.
1. Now what is the area of the original function of the converging function just from 0 to 1?
0.
There is no
0.
function, there is no, you understand? So this is going to be equal to how much?
0.
0. And 0 is not equal to 1. Yeah? Does it make sense? So we had to make several mistakes. That's how we learn in life, right? When you are a little baby, you fall down a lot, right? Till you learn how to walk. All right, so that was problem number D. Let's do one more problem from chapter 5, guys. If you want me to tell you, the easiest one is C as in Charlie.
Yes. So let's do D then.
Should we do C or D, guys? This is an if and an if. So you know x equals the naturals. These natural are all subsets. Mu is the counting measure. What else? That's it. Show that f is in L if and only if the sum of Fn is less than infinity. That sounds like an easy problem. Right. So if I find this problem like this, I should be able to do it with no problem. Well, provided we understand it today, right? So, what does F in L means? F in L means what? F in L, like. So we know, what do we know here? We know F in L, right? Which means what? Let's probably just do F in L implies the absolute value. The absolute value, what happens to the absolute value? In other words, the integral is finite. Right? Yes or no?
Yeah.
Or let's do it the other way around. Infinity is greater than f linear, yes? Or let's do it the other way. See, that's why I don't like you to write. See, because we're going to be erasing a lot. It's better that you understand what's going on, right? I know you're writing. I know. You know I'm talking to you, okay? You know I'm talking to you. Yes? And what is the integral of a function?
The integral is positive.
This is, let's write f by what the heck is f? Well, I don't know f, but it's f is, what is the value of this function when n equals 1? Because my universe is natural. What is the value of this function when n equals 1?
Just that.
What is the value of that function? So that function evaluated at x is f of x, right? Equals, but what is the value of x? 1, right? Yes or no? Now what is the value of the same function when x equals 2? Absolute value of f of 2, right? Yes or no?
Yes.
So I know the function. So it has this value when x equals 1. It has this value when x equals 2. So let me write it slightly different. So this function is equal to this guy when what?
X is 1.
How about when x is in this set? Yes? And this, so it has lots of values, right? Yes, you see what I mean? When x is in this set, yes? In other words, it's a simple function. It's almost like a simple function, right? Because it has cases. When you do cases, that's a simple function, right? So therefore, a function is this guy times the characteristic function of 1. Because when x equals 1, it's this guy plus yes, plus blah blah blah, right? In other words, this is the same as sum of f of, now we need a number, a variable, n equals 1 up to infinity times the characteristic function of what? N, right? The mu, right? All right. So, and so the infinite sum is the limit of the partial sums, right, guys? This is the limit the partial sums. How about if we, instead of n, I don't know who chose n, but I should have chosen k, because that reminds me of a girl whose name was Carla.
How many girlfriends did you have?
Of some,
Oh, finite, right? Finite amount.
almost everyone, man.
Almost there.
So we're almost done. We're almost done. What can we do with these symbols, guys? These two symbols.
Switch.
Flip them, switch them. Thanks to a theorem. When can we flip those? What is the name of this theorem that says, oh, you can, the integral of the limit is the limit of the integrals?
Where did the characters go? Did you ignore the characters?
No.
Oh,
Daniel, you're very picky, Daniel.
I'm sorry, I'm too picky.
So this is, what is the name of the theorem?
MCT.
Monotone convergence theorem.
Which theorem?
Because these guys are, this is
They're
this is
partial
increasing, right?
Yeah, okay, just right now.
And so by the monotone, this is the limit
But I got.
n approaches to infinity, integral sum k equals 1 up to n.
Good with that.
And then you can make that.
Did I hear like school doctor, right? All right. And so this is a finite sum, right? So what is the integral of f plus g when you have only two functions?
Sum of it.
The integral of f plus the integral of g, right? When you have three functions, that's the same thing. When we have a finite amount of functions, that's the same thing. So this is the sum. So these two symbols, you can switch them because that's a finite amount. You don't require any theorem. So this is just the sum of the integral of this guy times this indicator d mu of k equals 1 up to n. And here was someone to ask some of the people who always are copying super fast, okay? I'm going to change this into a, like a number. I'm going to change this into a set. And what is this integral? This is an easy integral. Juan, what is this integral? This is an easy integral, Juan.
It should be.
Shh, are you Juan? God.
I was thinking of the set, but yeah, sure, it's that 8 times the measure of E.
8 times the measure of E, yes? You guys agree? Yes or no?
Yeah.
Yeah.
So, what was here? A, what was here?
Absolutely, okay.
Okay.
And here was the singleton K. So what is this integral? This integral is absolute value of f of k times the measure of the singleton k, alright? So I'm going to ask Ted, how much is this, the measure of this set? Ted. Only Ted can answer, right? No. What is the measure in this problem?
The right one?
It's a counting measure. So you count how many elements are inside and that's it. How many elements are in this set? Listen, singleton. How many? One. Only one element. Look, it's k, right? So that's one. Yes? So therefore, the final answer is the limit as n approaches to infinity of the sum of what? F of k times 1, which is that, from k equals 1 up to n. But the limit of the partial sums is the infinite sum, right?
Yeah.
So therefore, that guy is less than infinity, right? Conclusion, infinity is greater than the sum from n equals 1 up to infinity of f of n. I know some of you complain, say, why did you write here K? But you write here, you write N. And the answer is because that reminds me of a girl who was Nancy, right? That's a dummy variable, right? And the other one is exactly the same way. So I'm just going to leave that one. The other one, you do it exactly in the same manner.
What, yes, the other way?
Yeah, the other way.
Do you really have to show much the other way? Doesn't it pop right out of the assumption?
Yeah, it's just the same
Like
thing.
just write down the assumption and say, therefore.
Yeah, something like that. You guys get it? Yeah? Robin?
Oh, I'm
So-
just trying to see the other
So
way.
therefore infinity
Yeah,
is
that was-
greater than.
That's good, yeah.
Right? Alright, now for the other one, you go, so I know that this is, so infinity is greater than what? And the sum of fn, right? From n equals 1 up to infinity, which is equal to what? Just work it out backwards, right? So you can even save some steps, right? This is equal to that, this equals to that, this equals to that. By the monotone convergence theorem, I should have not erased it. But do you agree that this equals that?
Yes.
This equals that because the integral is, this is 1 and this is 1.
Aren't we also assuming here that the integral of f equals the sum of the fn's?
Yes.
So can't we use that to get it?
No. No, because we need to show that I think you're saying that this is the integral of f, right? But I think we need monotone convergence theorem.
To get there?
Yeah.
Okay.
So you just work it backwards, right? This equals. And therefore, you achieve that this is equal to, what was the other one? Integral of f dv. So therefore, what's the conclusion? The integral of f is less than infinity. In other words, f is in L.
So
Yeah? Yes, Jordan.
in the first one, when did we actually show that the integral of f equals the sum? So we showed the integral of the absolute value equals the sum of the absolute values.
Oh, yeah.
You know what I'm saying?
Yeah.
Can we, at what point can we get to actually?
Okay, no, we just proved the if and only if.
Yeah.
No, well, we just proved that. Yeah, sorry, I forgot that.
And then can we, with the if and only if we're just working straight backwards, can't we go if and only if the whole way? Like, I don't see a place where it breaks.
No, yeah, you're right. You're right. So what Jordan is saying is that instead of doing 2 arrows, let's do just if and only if and only if and only if. Is that okay, guys?
Yeah.
You see what I mean? So, yeah. So we reduce everything in half. You see what I mean, guys?
Yeah.
So you do instead of 2 arrows, you do if and only if and only if and only if. Right? Does it make sense?
Yeah.
All right. So, and Jordan is saying we're missing a little piece. What is a little piece of miss? What
That
is
the
it?
integral of f d mu equals the sum of the fn's.
Yeah. And it says in any case, right?
Yeah. Here you go.
No, I got it.
You got it?
In which case, so okay, now that we know the if and only if, the second part of the problem says, in which case, show that in this case, so that if f is in L, then the integral of f d mu is equal to the sum of fn.
Yeah. Because we did show already that the integral of the absolute value equals the sum of the absolute value of the fn's, but I didn't know how that was going to help.
Okay, so therefore, so I say, So now we know. That f is in L, right? Hence, its integral is finite, right? Infinity is greater than the integral of f d mu. Yes?
Yeah.
And this is equal to f plus d mu minus f minus d mu. But what is f plus? Is the sum of f n from n equals 1 up to infinity, f plus times the characteristic function of n d mu. Again, we do the same trick. Minus the sum from n equals 1 up to infinity, f minus n, the characteristic function d mu. And because now we know that this is greater than or equal to 0. By the MCT, this is the sum of the by the MCT, because everything is greater than or equal to 0. F plus n, characteristic of n d mu, minus the sum of f minus n, characteristic function of n. No, integrals, right? Yes or no? Oh, by the way, what the heck is this integral? This integral, we can easily do it because that's like a simple function. This is a number and this is a set. So this is not a function. This becomes a specific number. So we can do it. So this is the same as f plus n times the measure of that, which is 1, minus f minus of n, and then we combine those sums. Why can we combine those sums? Why? Because this converges absolutely, so that means the sum without the actual values also converges, so it's finite. Or you can split it as two sums here, because this is one minus the other one. So in other words, we can combine these two series, and what's the answer? Maybe we just combine the series. What is it? F plus minus F minus, which is F, right? Yeah. So maybe that's how it works. Yes? I suggest, I'm getting tired, and if we do one more problem, can we go home, guys?
Yeah.
Yeah? Okay, so show that if the integral, if this limit fn minus f d mu is equal to 0, show that that implies that the integral of f d mu is equal to the limit of fn d mu. So now I'm doubting this problem. Let's see where the proof, where we get stuck. And so this is like these are numbers. These are finite numbers. These are like numbers in the like real numbers. And this is might be infinity. Do you guys agree this might be infinity?
Yeah.
So this is A in R extended. So but in general, AN okay, so I think we do two cases. I think now I see it. So what if that is equal to infinity? What if A equals, what if this integral if this integral is equal to infinity, then we are done. Why is that? Then by phi2, what is phi2? The integral of f v mu is less than or equal than what? Phi2. This is where you help me, guys. The integral of a function is less than or equal than the lim inf of the integral
Sequences.
of what? Fn v mu. Yes?
Mm-hmm.
Why? How do we know that? Because Fn converges to F, so therefore the absolute value of Fn also converges to F. But because this limit exists or not? Do we know that? Well, we know that this is equal to infinity, right? Yes? Or no? And therefore, if this limit inferior is less than infinity, look, this is less than or equal than the lim sup, yes or no? But the lim sup of whatever is less than or equal to infinity because I don't know anything bigger than infinity. Do you know something bigger than infinity? No. So anything is less than or equal to infinity. You guys agree?
Okay.
So therefore, by the squeeze theorem, what can you conclude by the squeeze theorem?
But then don't we also assume that the limit of the the hypothesis says that it's finite, it's equal to 0?
No.
And
So-
then Fn minus F absolute value.
Oh,
is-
that one is equal. Yeah. that
Yes,
one-
but it's the absolute value of Fn minus F is less than or equal to the absolute value of Fn.
Yeah.
Yeah,
Yeah.
it's like this one is for sure bigger than this.
Well,
So this is squeezed to be 0.
just by phi2s, can't we stop at the limit? If the limit is greater than or equal to infinity, it's gotta be infinite, right? Like we
The limit is So this is like an extra
Extra,
form of thing.
okay.
So by squeeze theorem, what do we conclude? That all of them are equal to infinity, right? But if the lim inf matches the lim sup, that means the limit exists. You guys agree? So therefore, we conclude that the infinite, they all match, and this can be replaced by the limit.
So
Yes?
we-
And by the way, we have something extra. This is equal to infinity, but we don't care. We don't. Yes?
So we need that step to show it exists. Kind of?
I guess, yeah.
Okay.
So I think we finish. So how do we finish this case? So what is the main tool to finish this case? Phi2, right? That's it. You guys agree?
Plus common sense.
Plus squeeze theorem, but squeeze theorem is like,
Yeah.
everyone knows squeeze theorem, right? You guys agree?
Yeah.
So that was case 1. Can I erase it, guys? Yeah? Is the camera still recording? Okay. All right, let's do case 2.
So case 1, we didn't even need our assumption, huh?
I think we needed this one.
Yeah, but not the,
We don't need that one.
or the other one.
Yeah.
Okay.
Yeah, we don't need that and that. You see what I mean, guys? So maybe I can put a problem in there. I can put something in. I can just create a new problem. Say, show that this and this implies that. You see what I mean, guys? Because we didn't need Why? We didn't need this one either, right? So show that,
No, it's okay, you can keep it all.
this implies this, right?
Yeah, but it's not gonna hurt to have other pieces too.
Yeah, do you guys agree? All right, now, but what else do we have here? Fn is in L, and we know that the limit, and as n approaches to infinity of the integral of Fn minus f is equal to 0, right? So show that. Okay. All right, so now let's do case 2. What was case 1? I forgot what was case 1.
That was infinite.
The integral of a was infinite. What's case number 2? The integral of this is finite. So this time, I know that this is finite. So that's a real number. You guys agree? Now, how do we prove that? This is like a calculus question. How do we prove that the limit of an equals a when n approaches to infinity? How do we prove that?
So for all epsilon greater than
You can do
0,
for all epsilon, blah, blah, blah. Right, guys? Yes. So what I'm going to do is I'm going to do so I'm going to observe an minus a and see what it is. So by observing this, you see, this is what I want. A equals the limit of an, right? That's what I want, right? You see what I mean, guys? So the way I'm going to attack it is by observing this. That's it. So observe or notice or consider an minus a. What is it?
Fn minus.
An
the
is
integral.
the integral of Fn d mu minus
The integral of the absolute value.
actually I want to consider this absolute value minus the integral of f. So not that one. I lied to you guys. I'm sorry. I'm not going to consider. I'm going to consider an minus a. All right. So this is equal to. I can combine these two integrals into a single integral. What is it? Integral of Fn minus f absolute value mu, and I can bring this absolute value less than or equal the integral of absolute value of absolute value minus absolute value. 3 absolute values here. What the heck?
It's gonna be,
And then we use the reverse triangle inequality. Gosh. Yeah,
it's gonna be non-negative for sure,
Yeah, so this is less than or equal than Fn minus f.
And that's a hypothesis that equals 0.
No.
No?
But it
Oh,
takes
the
limit.
limit, yeah.
Now say take limits. So take limit here. No. Okay. So let's do consider, right? Before taking limits, I want to say this is greater than or equal to 0, right? Now take limit here. 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 And by hypothesis, how much is that limit? 0, right? All this becomes less than or equal. And so the limit of 0 is 0. Therefore, by squeeze theorem, you're hungry one. So 0 equals the limit as n approaches to infinity of Fn d mu minus the integral of f d mu equals equals 0, right? Yeah. How did I call these guys before? How did I call this integral? A-n. How did I call this? A. So what we proved is that the limit, or let's call this B, let's call this Bn, how's that, guys? So we proved that, hence, the limit of Bn, the absolute value of Bn is equal to 0, right?
Oh, that's true of Theorem.
Yes. Hence, if the limit of the absolute value of something is equal to 0, the limit without the absolute value, what do you guys think? It's equal to 0, right? So we can go ahead and remove the absolute value. So what is this integral without the absolute value? What is that limit without the absolute value? Well, let's replace Bn by what it is. So what is, therefore, the limit? What is Bn? An minus a, right? Yes. This limit is equal to 0. But the limit of the difference is the limit of the difference is the what? No. It's the difference of the limits, right? Yes or no?
Yes.
But the limit of a constant is a constant itself, right? There is no n. So therefore, the limit of an when n approaches to infinity minus a equals 0. Therefore, that limit equals a. And that's what we wanted, right? That's what we wanted, right? That's just like calculus limits properties, right, guys? It's mainly. All right, so I guess this is it. There is only one problem that we couldn't do. Not because we couldn't do it because we were like dumb or something. It's because we didn't have time. Do you guys agree?
Yeah.
So, but I trust that you guys can do that one. That was problem 4.
I.
4C.
Yeah. But
Oh,
it's
that's
I from
so
the book.
freaking easy. I mean, how do you compute the integrals of a number times the characteristic function? It's just so easy, right? You guys agree?